All right, so this is our first presentation for the course. It goes over overviews and concepts. So in this module, we're going to walk through an overview of potential failure mode descriptions and event tree analysis. We're going to be working through a general event tree framework to identify the elements of a PFM description, understand how to decompose those parts into key events that we use in event tree analysis, and then describe some event tree rules. A quick outline of the presentation: start with an overview, move into PFM descriptions, and then those terminology and rules for event trees that we just discussed. So first, we need to overview a few fundamental concepts that are needed to understand how we go about building event trees. So the first is to define a potential failure mode. A potential failure mode is a unique set of conditions and/or sequence of events that could result in failure or breach of a dam or levee embankment. Failure in the dam and levee safety programs is characterized by the sudden, rapid, and uncontrolled release of impounded water as defined in FEMA 148, and FEMA P1025 expanded the definition of failure to include the words liquid-borne solids, such as mine tailings and dredge spoils. According to FEMA 148, it's recognized that there are lesser degrees of failure in that any malfunction or abnormality outside the design assumptions and parameters that adversely affect a dam or levee's primary function of impounding water is also properly considered a failure. These lesser degrees of failure can progressively lead to or heighten the risk of a catastrophic failure. They are, however, normally amenable to corrective action such as successful intervention. So other failures that result in loss of service or damaged states that affect the operability of our projects, they're also considered for high hazard potential dams and significant hazard potential dams such as run-of-river lock and dam projects. Now, these PFMs are those which could have significant economic consequences, but they don't carry any life safety risk. So loss of service PFMs are also sometimes associated with hydroelectric power plants. A potential failure mode description captures the events that are required for the potential failure mode to reach a designated failure state in narrative form. There are three elements of a potential failure mode description: the initiator, the failure mechanism, and the resulting impact on the structure. The initiator is related to the hazard, and it can be a reservoir or a flood load, an earthquake, degradation or deterioration, or malfunction or improper operation. The failure mechanism, including the location and/or the flow pathway, is the step-by-step progression to reach from initiation to failure or breach. And then lastly, the resulting impact on the structure is described, including the rapidity of failure and breach characteristics or damage state. A well-written PFM description is essential to an in-depth risk assessment. The PFM description steps through the chain of events that lead to failure or breach, and it should include enough words to describe each discrete event, but nothing more and nothing less. The description should clearly identify and focus on the weakest link or area where the potential failure mode is the most likely to occur, and also provide the critical load level and annual exceedance probability for a semi-quantitative assessment, or thresholds or trigger elevations for adverse performance for quantitative assessments. We're going to get into some more detail on the elements of PFM descriptions later in the presentation, but this is a really good starting point for us, and we're going to come back and continue to reference this slide throughout the presentation. So next, let's get into a quick overview of event tree analysis. Event tree analysis is an inductive modeling technique that uses Boolean logic, i.e. true or false, to evaluate a sequence of events. An event tree is a graphical depiction of the sequence of events leading to a particular set of outcomes. Its construction is sequential from left to right, and it begins with an initiating event and proceeds with all necessary subsequent events in the order that they occur. So because event tree analysis is an inductive type of analysis, logic moves from cause to effect. Outcomes for dam and levee safety risk analysis are typically breach, uncontrolled release of impounded water or liquid-borne solids, or non-breach, each with associated life loss and economic consequences. And that's really the focus of this training course. However, outcomes can also include a specified damage state, an example of which would be the Oroville spillway incident from several years ago that doesn't result in an uncontrolled release and life loss potential, but it can result in significant economic consequences. Event tree analysis is the most common approach for estimating dam and levee safety risks. Complex potential failure modes can be decomposed into more understandable sequences of events, and event trees assist in the understanding, analysis, and communication of dam and levee safety risks to decision makers. This slide walks through a general event tree framework for risk analysis. There are three elements that comprise the general event tree framework: the hazard or loading, performance or system response, and consequences. Each of these elements contain a suite of sub-elements that are broken down in more detail. So we begin with the hazard or loading variables, starting with the initiating event and then accounting for any additional factors that affect the loading, such as gate reliability or debris blockage. This element is analogous to the initiator element of the potential failure mode description. From the loading, the tree proceeds to the performance or system response, which represents the potential failure modes that are being evaluated for a given project and is analogous to the failure mechanism element of the potential failure mode description. The performance element consists of component performance, performance intervention, and failure sub-elements. Each potential failure mode will have its own sub-event tree that is composed of a step-by-step failure mechanism required for failure, which we'll discuss more in detail later in this presentation. And from performance, the tree progresses onto the consequences given that a failure has occurred. This element, as well as the failure sub-element from the performance, is analogous to the resulting impact on the structure in the potential failure mode description. So pay attention to this general event tree framework because we are going to be referencing this throughout this presentation. We have a few interactive knowledge checks where you're going to have to match up some of these sub-elements with the main elements in the framework. When we're discussing event trees, there's two types of event trees that we need to differentiate: sub-event trees and project event trees. Both types of trees are important for risk analyses, but they play different roles. Sub-event trees are used to evaluate individual potential failure modes and their conditional probabilities of failure within a risk analysis. They use Boolean logic, true or false, to evaluate a sequence of events like we discussed previously. But they only evaluate performance or system response of a structure from the general event tree framework, and they represent the step-by-step failure progression to failure or breach for potential failure modes. Now, project event trees, on the other hand, are used to represent multiple PFMs and total project risk for a single structure or system of structures. They incorporate all the elements of the general event tree framework, the hazard, the performance, and consequences, and they serve as the blueprint for risk calculations. So Module 2 is going to go more in depth on sub-event trees, and Module 3 will go more in depth on project event trees. But now let's go back to our potential failure mode description. The following slides are going to go into more detail on each of the elements of those PFM descriptions within the general event tree framework. So back to our first element, the initiator or the hazard. This is the event that's going to drive the failure progression. It's the push, so to speak, that gets the ball rolling. The most common type of initiator for dam and levee safety is hydrologic, A hydrologic hazard is caused by impounded water load or its outflow for dams or a flood load for levees. Another common type of initiator is seismic ground shaking for some of our potential failure modes. So seismic initiators they're more prevalent along the West Coast and in the central United States where ground motions are the strongest. However, the seismic loading should be checked for all structures during a risk assessment regardless of location. A third type of initiator or hazard is degradation of one or more project components that leads to or contributes to failure or breach. Examples of degradation can include fatigue, scour, chemical reactions such as alkali aggregate reaction or alkali silica reaction, AAR or ASR, or corrosion or section loss that causes deterioration of a structure. Degradation can lead to a deteriorated condition such that a structure will fail under a routine operating load, or it can be a contributing factor to failure alongside a hydrologic or a seismic hazard. And then our final type of initiator or hazard is a change in static loading. This refers to any change in static loading that's experienced by the structure, such as additional load at the crest of an embankment due to construction activities, replacement of spillway bridges or gates with heavier structures than were originally there. And just as with degradation, changes in static load can cause failure of a structure during routine operating load, or it can be, again, a contributing factor alongside a hydrologic or a seismic hazard. Remembering back to the general event tree framework from earlier in this presentation, the hazard or the loading element also captures an operational performance element or sub-element that can serve to exacerbate the initiator. As an example, malfunction or improper operation for a gated spillway can occur due to the failure of gates to operate on demand from mechanical, electrical, or other gate component failures. Similarly, malfunctions of remote gate operating systems can also prevent gates from opening when needed. Other examples could include loss of access to the gate controls due to a rising reservoir elevation, inadvertent gate closures due to inundated breaks, general overfilling of the reservoir for hydropower purposes, or human decisions or factors such as a deviation from the water control manual. The human element can play a large role in improper operation, again, with an example being that Oroville Dam incident in 2017. Another example of operational performance for a dam is spillway plugging, usually due to debris blockage. Debris can become caught in the gate bays and can reduce the spillway capacity, which will result in a higher peak stage or peak pool than what would normally have occurred. The resulting impact on the hazard is captured in the figure on the right. So these are stage frequency curves for a dam with differing amounts of spillway capacity reduction due to debris blockage. The more debris blockage and capacity reduction, the higher the peak stage for a given annual exceedance probability. So the impacts on the stage frequency curve for this example are significant, and it highlights the kind of effect that these operational performance elements can have on the hazard. Operational performance can also affect levee systems. Interior drainage features, such as pump station malfunction, can result in reduced pumping capacity of the system and flooding of a levied area prior to any breach of the levee system occurring. So operational performance is not dams only, it affects dams and levees. All right, so this brings us to our first knowledge check. We want this to be an interactive course, so we're going to test your knowledge so far. On this slide, we have the hazard element and sub-elements from the general event tree framework. So I'm going to turn on the annotation feature within WebEx, and what I'd like you to do is match the items at the bottom of the slide to the initiating event, operational performance, and operational intervention sub-elements above. So annotation should be turned on. So why don't you take a minute, you can draw on your screen, use your mouse, whatever. to draw lines. Several of you are already doing it, to draw lines from the sub-elements to the elements above. It's going to get a little bit messy, but hopefully it's a worthwhile exercise. So I'll give you a minute to go ahead and draw. All right. Well done. Appreciate everyone participating in that. I especially like somebody circling. Oh no, that's just a very long line from portable pump all the way over to the sub-element. That's good. All right. I'm going to go ahead and turn off annotation. Get rid of them all. All right. So here's the solution to that knowledge check. I think all of you did pretty well with that, with each sub-element of the hazard color-coded to show you where they should be matched. So we have our change in static load, seismic, and hydrologic that are matched up with our initiating event, our interior drainage features, spillway plugging, and malfunction or improper operation matched up with the operational performance sub-element, and then portable pump, debris removal, and component replacement that are matched up with our operational intervention. Once the initiator for the potential failure mode has been identified, the failure mechanism must be developed in detail. So now this is our second element of our potential failure mode description. The failure mechanism is where we define how the structure is going to fail, and it's synonymous with the system response component of the general event tree framework that we discussed earlier. The failure mechanism begins with some type of component performance given the hazard, such as backward erosion piping, overtopping, slab jacking, or structural spillway failure. A step-by-step progression of events that lead to failure follows next, including unsuccessful intervention to slow down or prevent a failure from occurring. And then finally, the failure mechanism will be punctuated by a breach or failure of some sort. I want to emphasize that this step is critical in the development and evaluation of a potential failure mode. If a PFM isn't well defined and understood by the entire risk assessment team, the evaluation won't be consistent and the results won't make sense. When developing a failure mechanism, the question you should be answering is, what must happen for the end event of interest to occur? This requires that you be specific. The overall failure mechanism should be clearly identified in the event tree and potential failure mode description. Using generic terms such as internal erosion, monolith instability, those are not sufficient. Instead, we should use the established and specific failure mechanisms such as backward erosion piping, concentrated leak erosion, etc., when describing internal erosion failure modes. The same principle applies to potential failure modes for other disciplines. Generic terms such as concrete spillway failure doesn't describe how the concrete spillway is truly failing. Instead, use terms such as external monolith instability and sliding, slab jacking and spillway erosion leading to monolith overturning. Use terms like that to describe the mechanism by which the structure will fail. With your overall failure mechanism identified, your next goal is to produce a step-by-step progression of events that must occur in order to lead to that end event of interest. This is perhaps the area that most leads to inadequate potential failure mode descriptions and event trees. The goal of the step-by-step progression, in a way, is to tell a story of how the structure will fail. So you might be thinking there's a reason that you pursued engineering, geology, economics instead of becoming a professional writer, but that shouldn't stop us. It's our job to tell the story, and there's a few things that we can do to make that process a little easier. We need to start at the beginning and continually ask ourselves, then what? or what next until we reach the end of the step-by-step progression. Many times we tend to try to combine events in order to simplify our analysis or evaluation, and many times these simplifications are well understood and accepted, but we need to fight the urge to do this when we're telling our step-by-step progression story. If we do it right, we'll end up with a descriptive step-by-step recipe of how the structure will fail, starting with initiation and extending all the way through failure or breach. It's important to remember that the description will often be the first interaction with your potential failure mode that decision makers are going to have. So it's imperative that we tell that story well. So this slide is meant to be a simple and lighthearted example of our tendency to simplify and combine several events into one. We have a process that we call baking a cake. If you're familiar with the Great British Baking Show, you've seen this in action. Many times the contestants will be provided with a bare bones recipe for cakes or treats that they've never heard of. And when it comes time to put their items in the oven, they're only provided with one word, bake. They're not given a temperature, they're not given a time. Most everyone will know exactly what we're referring to when we say, I'm baking a cake, but in reality, there's a progression of steps that have to occur for that goal to be achieved. We need to turn on the oven. We need to gather and combine the ingredients, pour the cake batter into a pan, put the pan in the oven, set a timer, etc., until we have a finished cake that's ready to serve. Now, imagine that somebody's baking a cake for the first time. If an instruction sheet was left for them that only says bake a cake, they won't know where to start or how to finish. Conversely, if they're handed an instruction sheet that has one or two steps missing, they're likely to be left in exactly the same spot. If they're not told to turn on the oven, their batter's going to sit uncooked forever. If they're not told how to properly gather and combine the ingredients, the cake won't bake correctly. If they're not told to set a timer after they put their cake in the oven, they'll end up with the fire department at their house. It's important that the full step-by-step instructional process is left for them so that they can successfully navigate from start to finish. The same logic applies to a step-by-step progression for a potential failure mode. As I said previously, the description will be the first exposure that a decision maker gets to a potential failure mode, so it's imperative that they be given a proper breakdown of the steps that are required to reach failure. And if any of those steps are missing, the result won't make sense. So I see a question in the chat. This level of PFM definition occurs even if the PFM is eventually screened out before an SQRA. And Gabriella provided a response. It's not required for Appendix A or the excluded failure mode appendix, but many times can be a useful guide to writing why the failure mode is screened out. So that's exactly right. So every failure mode, we need to really define the failure mode, even if it's going to be screened out. You don't go to the same level of detail writing the potential failure mode description and formulating an event tree for excluded failure modes, but the process you do need to go through the process so that you can fully understand the failure mechanism and then fully be able to describe and justify why it was excluded. And Manal has reminded me that I have a step missing on my step-by-step progression here, which is to eat the cake. So, of course, serve the cake and then eat the cake, or eat the cake without serving the cake, whichever you want to do. In addition to the step-by-step progression for the potential failure mode to get to our end event of interest, we also need to specify the location where the potential failure mode is the most likely to occur. Discretely identifying our PFM location will allow the risk assessment team to gather the pertinent data specific to that location and will provide clarity for the potential failure mode moving forward. Make sure that the location of the PFM is specified with a station, river mile, or other geospatial reference. There are several ways to identify the most likely location for a PFM. Areas of past poor performance or observed distress are big markers for locations of potential susceptibility. The result of routine monitoring and inspection activities can also provide indications, such as areas of historic seepage that could be vulnerable to internal erosion, or embankment low spots that will begin overtopping and lead to overtopping erosion more quickly than other areas along the embankment. Instrumentation can also provide potential locations for PFM, such as an area where foundation seepage pressures are trending upward and may indicate deteriorating foundation conditions. Finally, project vulnerabilities can also be used to identify locations for potential failure modes. Examples of project vulnerabilities could be weak foundation rock layers that are susceptible to sliding for concrete monolith stability PFM, zones of loose foundation sand that are susceptible to liquefaction, maybe for a seismic slope instability PFM, concrete spillway slabs that contain known gaps or offsets for a slab jacking and spillway erosion PFM, or areas of the embankment that are shown to be weak links based on analysis results. All of these things can help us to hone in on a location for our potential failure modes. All right, now we have another knowledge check. We're doing the same thing that we did for the previous knowledge check, but for the performance or system response element on the general event tree framework. So go ahead and annotate, draw your lines. All right, looks like most everyone's definitely on the right track here. A couple of people are tired of the line drawing and just want to draw smiley faces and say howdy. That's nice. All right, let's clear all of these, turn that off. Yeah, so here's the solution to knowledge check number 2, and I think most of you nailed that one pretty well. Overtopping erosion, monolith instability, and internal erosion all get matched up with our component performance. Reservoir drawdown, reverse filters, and sandbag rings are matched with performance intervention. And then damage state or breach, uncontrolled release get matched up with our failure sub-element. All right, that brings us to our final element in the potential failure mode description, the resulting impact on the structure or the end event of interest. The first step of defining the impact on the structure is deciding what that impact actually is. Most commonly for flood risk management infrastructure, the impact of the potential failure mode being evaluated is failure or breach of the damming surface that leads to an uncontrolled release of impounded water and potential life loss. However, as we discussed before, there may be other adverse consequences that result from a potential failure mode that are not tied to life loss, but are tied to economic, environmental, or cultural damages. Examples of other adverse consequences include major spillway erosion without breach, failure of a lock gate on a navigation structure that leads to loss of navigation, or failure of a powerhouse penstock or turbine leading to loss of power generation for a hydropower facility. The breach mechanism must also be identified, not only the method of breach, but the breach mechanism for a specific potential failure mode. So a common example of a geotechnical or hydrologic breach mechanism is overtopping erosion during an extreme or due to an extreme hydrologic event. Other examples could be tied to the breach mechanism, the 4 breach mechanisms associated with internal erosion, gross enlargement of a pipe or a concentrated leak, overtopping due to crest settlement, sloughing or unraveling of the downstream embankment face, or slope instability. One or more of these mechanisms may occur during the breach process, and they can occur during the same breach process. So you could have gross enlargement that leads to sinkhole development or slope instability that results in overtopping. So don't get too wrapped around the axle trying to figure out precisely which mechanism or mechanisms are occurring, but it is important that you have a general idea of how the breach will form. A few more that are on the slide here. In addition to the geotechnical breach mechanisms, two common structural breach mechanisms are sliding or overturning of concrete structures, such as spillway monoliths or flood walls, or overstress failures, such as gate arm buckling or radial gate anchorage failures. All right, and then the final thing that we have to define for our impact on the structure is the magnitude and the size of the end event for our PFM. Will we have a full or a partial breach, for example? For a dam event, the size of the breach can be affected by the erodibility of the embankment materials, lateral erosion boundaries, such as a rock abutment or concrete spillway, or the size of the reservoir and the time available for breach development. Full or partial breaches can also apply to concrete spillways and even spillway gates. For a concrete spillway potential failure mode, are we looking at one or more full spillway monoliths becoming unstable? Or is there a partial height monolith breach due to sliding at an internal lift joint? For spillway gates, is there a full breach where the gate becomes completely detached from the spillway structure? Or will we have a partial breach where the gate doesn't come completely unzipped? For a multi-gate spillway, how many of the gates are going to fail? For a levee or a flood wall breach, how wide will the failed section be? This can be based on geometry or structure type, i.e. flood wall versus earth embankment, or other factors that limit breach size, such as those we mentioned previously for dams. Levees breach differently than dams, and it's important to remember that. Levee embankments typically reach full breach depth relatively quickly, and then they continue to widen, resulting in breach width to depth ratios that are much greater than what we typically see for a dam embankment. Additional considerations for levees are the flood duration and whether the leveed area fills up like a bathtub. And these are perhaps the two most important factors to consider when evaluating consequences for a levee failure. If your end event of interest is a damage state that impacts operability, such as spillway damage, then the extent and magnitude of the expected damage must also be assessed. Now, whatever your breach method, mechanism, or magnitude, the consequences in your risk analysis must be consistent with that end event. A consequences model for a full spillway breach should not be used if only one monolith is expected to slide. Conversely, a consequences model for an appurtenant dike shouldn't be used if the main dam is being evaluated for failure. If the consequences are not consistent with the end event specified in the description, qualitative adjustments of the consequences model made by the risk assessment team will result in a high level of uncertainty and a likely over or underestimation of the consequences, which ultimately will lead to a corresponding over or underestimation of risk. All right, let's do this one more time for our consequences element. So go ahead and draw your lines matching up exposure and losses. All right, very good. I think most everyone matched these up pretty well. So for our exposure, we have time of year, evacuation, time of day, flood characteristics, day of the week, warning. And for our losses, we have economic, life, cultural, and environmental. So well done. All right, now that we've covered our potential failure mode descriptions and the elements that go into a complete PFM description, We're going to go through an overview of event tree analysis and discuss some common event tree rules and terminology. Every event tree begins with an initiating event shown at the left side of the tree. That's represented by our flood in this example. The initiating event is commonly defined as a continuous function and is portrayed by a fan symbol. We're going to discuss continuous functions and loading variables in Module 3 of this course, but the takeaway for now is that the fan represents the full range of intervals that the variable can take on. And when I say a fan symbol, I'm referring to this symbol right here. So in this case, our fan represents the full range of flood loading that we're evaluating, from our lowest reservoir level all the way up to our maximum reservoir level. In our example that we have here, the initiating event of a flood loading is then broken out into two separate flood intervals that together comprise the entire range of loading. Each branching point of the event tree is referred to as a chance node. Chance nodes are branching points at which a new random variable is introduced into the tree. Branches and their associated branch probabilities emanate from each of the chance nodes. The branch probabilities represent the probability of the event or the branch conditioned on occurrence of those events that precede it or are to the left of it. We'll discuss conditional probability a little bit more in a few slides. The last nodes at the rightmost side of the event tree are end nodes, which are aptly named because that's where the tree ends. The end nodes are represented by triangles that are color-coded by result, with red triangles representing failure or breach, and green triangles representing non-failure or non-breach. In this example, the initiating event on the left side of the event tree is a flood, partitioned into two load ranges. For each of the flood intervals, a non-failure scenario and two failure scenarios can occur, as shown in the second column: non-breach, PFM1, and PFM2. A conditional probability of failure given the flood is assigned to each failure scenario within the event tree. Given that a failure or a breach occurs, the resulting consequences, in this case life loss, are shown in the last column. An event tree pathway is a unique set of events through the event tree that leads to failure or breach. So in this example, there are 4 pathways that lead to breach, with the bottommost pathway highlighted by a red line. Here's a short example of a potential failure mode description that we'll use to demonstrate how event trees are constructed. We're going to discuss this construction process more in depth in our next presentation, but this is just a simple example. Our key events for overtopping due to seismic crest deformation are shown in the PFM description. The initiating event is an earthquake with horizontal peak ground acceleration between 0.6 G and 0.8 G, while the reservoir has a stage elevation between 644 and 648 feet. The failure mechanism involves foundation liquefaction, slope instability that lowers the embankment crest, and overtopping with breach. So once our PFM description is complete, the potential failure mode can be decomposed into an event tree by extracting those key events. And then here we have that previous example, but in event tree form. The Boolean logic is illustrated by the event pairs shown where each event either occurs or does not occur. This applies only to sub-event trees for PFMs with binary responses or hazards, which have multiple outcomes. The inductive logic is illustrated by the sequence of cause and effect of events proceeding from left to right until breach occurs. Now, we said before, construction is sequential from left to right, beginning with the initiating event, proceeding with all necessary subsequent events in the order that they occur. The event tree doesn't need to be in chronological order from a mathematical standpoint, but a chronological construction improves the logic which can facilitate understanding and communication of the potential failure mode. So it's usually a good idea to construct the event tree in chronological order from left to right. So next we're going to discuss some basic event tree rules that we need to keep in mind as we're developing our event trees. The first rule is that all event tree probabilities must be greater than or equal to 0 and less than or equal to 1. So this is a pretty basic rule, but it's very important to remember. Our second event tree rule is that probabilities originated from a single chance node are summed, and the sum of those probabilities must be equal to 1. So let's look again at our example event tree. For flood interval 1, there are 3 branches that originate from the chance node: non-breach, PFM1, and PFM2. Probabilities for each of these events have been assigned for this example. Using the assumption that the events are mutually exclusive or independent, their probabilities are summed together directly. And as shown on the slide, the sum of those probabilities is equal to 1.0, which makes these events collectively exhaustive. This is meant to be a simplified example of these concepts, but the potential failure modes that originate from a given chance node are not always mutually exclusive. There may be overlap between PFMs such that summing them together would result in a sum of probabilities that's greater than 1. Now, in these cases, adjustments to the probabilities for these PFMs would need to be made in order to satisfy the requirement that they all sum to 1 and avoid overestimating the total risk. Now, these adjustments are beyond the scope of this training course. For more information, you can see DLS-105, Risk Tools and Calculations for Risk Assessments, but it's important to be aware of this concept when you're performing your risk calculations. Event tree rule number 3 is that the probabilities for each branch must be conditional on all preceding branches. In this basic example, probability B, or event B, is evaluated given that event A has already occurred, and event C is evaluated given that both event A and event B have occurred. So conditional probability is the probability of one event occurring with some relationship to one or more other events. Conditional probabilities are something that we deal with when working with event trees and pathways through those trees. The nomenclature for conditional events is a vertical line that separates the variables and can be read as either given that or conditional on. So the term in the second node would be read as the probability of B given that A occurs, because B is conditional on A. If A and B have a conditional relationship, then observing that event A occurs gives you additional information about the probability that B also occurred. An example of this could be the probability of a football coach punting on 4th down, which in most scenarios is going to be conditional on the number of yards needed for a first down. The lower the probability of a first down, dependent on the number of yards needed for a first down, the higher the probability that that coach is going to punt the ball. So the next slide gives a little bit more graphical example of conditional probability to further demonstrate the process. For this simple event tree, the probability of initiation, or node 2, must be evaluated as a conditional probability given that the flaw, or node 1, has occurred or is present. Following the same logic, the probability of progression, node 3, must be evaluated as a conditional probability given that the flaw and initiation both have occurred. And then this is carried throughout the event tree until we get to the end. Event tree rule number 4 is that probabilities for a branch can be a function of any transform variable or variables in preceding branches. Again, we're going to talk about transform functions when we get to module 3 of this presentation, but it's an important rule to establish here. In this example here, failure is a function of both stage and discharge. So perhaps we're looking at a dam conduit where the outflow is large enough to overtop the training walls and leads to erosion and slope instability. Then the only way that slope instability results in a breach is for the pool to be up and for the slide to be large enough to lower the dam crest below the pool. So failure in that instance is a function of both stage and discharge. All right, so now we have our fourth knowledge check, and we will be using Socrative for this. So go ahead and log into Socrative.com. Click Login, Student Login, and then our room name is DLS-107, and enter your name as last, first. So I'll give you a minute to go ahead and log into Socrative. And then when you get logged into Socrative, you should see, or you should be prompted to answer knowledge check number 4. So our question for knowledge check number 4 is, which of the following is not true for event trees? A is that probabilities for each branch must be conditional on all preceding branches. B, the probabilities for a branch can be a function of any transform variable or variables in preceding branches. Or C, probability estimates can be greater than 1 when the team is very confident. So go ahead and answer that question, and we'll get a verbal cue when we have a critical mass of responses. All right. Well, everyone's paying attention. That's good. Yes, our correct answer is C. So this is event tree rule number 1. I told you it was simple, but important. By definition, probability estimates cannot be less than 0 or greater than 1. It's a fundamental probability rule, and we cannot violate that rule when we're doing our risk calculations or event tree analysis. For all 3 elements of our potential failure mode description, and especially for the failure mechanism, a clear definition of our event descriptions is necessary for multiple reasons. Properly defined event descriptions help facilitate a common understanding of the potential failure mode by the entire team, and they enable development of an event tree or other means of estimating risks. Oftentimes, ill-defined event descriptions for potential failure modes leave room for individual interpretation by different members of the same risk assessment team, and this often results in confusion and misunderstanding. If all the members of the risk assessment team aren't on the same page when evaluating a failure mode, then the elicitation results and the risk estimate are not going to be consistent. They're not going to be representative of the failure mode that's being evaluated. Clear definitions are also important to allow for the formulation of effective and efficient risk reduction measures that target one or more nodes in the event tree, and to ensure that someone who picks up the risk assessment report in the future will have a clear understanding of the team's thinking. It could be a matter of years before our reports are picked up again, and the failure events and thought processes that were developed by the team during the risk assessment need to be clearly documented. In our next presentation, we're going to be taking a quick look at several examples of typical sub-event trees for different types of potential failure modes. And like I said at the beginning of the course today, we've developed a database of typical event trees that you can download and reference as you're performing risk analysis. However, while typical event trees are great foundations for potential failure modes that you may encounter, it's important that they be treated as starting points or as guides for the development of project-specific event trees. Each event tree needs to be customized to fit the needs of the specific project that's being evaluated, because each project is different. There is no true one-size-fits-all approach for event tree analysis that will work for every project. So ask yourselves the question, what makes this project unique? For internal erosion PFMs, do you have a zoned embankment? That might require a tweak to one of the nodes in your event tree. Is there a partial height filter that could lead to multiple exit conditions? For slab jacking and spillway erosion, is there a cutoff wall or a key underneath the control section that will need to be undermined before breach can occur? It may even be that multiple sub-event trees need to be combined in order to lead to a failure. For example, a dam embankment may be susceptible to slope instability from a seismic event, but the magnitude of the expected slide wouldn't remove the crest. So instead, the seismic shaking and slope instability may lead to transverse cracking and a shortened seepage path for concentrated leak erosion. The event tree needs to be customized to fit the project. So while generic or typical event trees are very good, they should always be used as a starting point to develop more specific event trees that fit your project. All right, that's the end of Module 1. Are there any questions from anyone? All right, so first question here is, should the PFM description include step-by-step progression, or are description and progression kept separate? No, the PFM description should include that step-by-step progression. The step-by-step progression is what's going to make up each node on your event tree. Each node will be represented by, or will represent a discrete event within your step-by-step progression. So you do want to include that step-by-step progression in the PFM description. Right. Is there a component of intervention in each major step, loading, system response, and consequences? So Gabriella has answered that one. Intervention is one node. It can be in different locations depending on the specific potential failure mode that you're evaluating. And we do have more information on how we handle intervention in the event tree construction process in Module 2. How is uncertainty built into risk assessments of impacts? Do we present risk consequences as ranges? And Gabriella answered that one. Yes, we normally look at ranges of consequences with a best estimate. So we perform Monte Carlo analysis using a program called LifeSim. So LifeSim will plug our dam break modeling or our breach modeling or hydraulic modeling into LifeSim, and LifeSim incorporates several different sources of uncertainty, from how the warning is disseminated, how long it takes for a warning to get out, how effective the warning is on getting the population at risk to evacuate. So there's many different uncertainties that are incorporated into LifeSim, and we do account for those in the risk analysis. In this diagram, how should we develop and document PFMs in formal reports? So yes, as Gabriella said, our event trees that we create, and we're going to be going through a quick overview of the RMC event tree toolbox after our next presentation. So those event trees that we create using that toolbox for risk analysis should be included in our reports. And our descriptions are included in our narrative PFM write-ups. So we will include both of them in our reports. How do you capture economic consequence uncertainty? So that's a good question from Adam. To my knowledge, we do not capture economic consequence uncertainty. So we have values for lost benefits for our project, or loss of navigation, loss of hydropower, recreation, that kind of thing. We have numeric estimates for property damage, direct property damage that occur from dam or levee breaches. But to my knowledge, we usually just apply qualitative judgment for economic uncertainty. So when we perform a semi-quantitative risk analysis, all of our risk estimates are order of magnitude. So they span from, for life loss, they might span from 1 life lost to 10 lives lost, from 10 to 100, 100 to 1,000. The same thing is done for economic losses. When we plot economic losses on a risk matrix, they will be order of magnitude estimates. So from 10 million to 100 million, 100 million to 1 billion, so on and so forth. So that is one way we incorporate uncertainty. When we perform quantitative risk analysis, uncertainty doesn't play a role in the quantitative risk calculations.
So, Adam, we have one more question at the end. Are consequences separated by economic, life, environmental, cultural?
Yes, thanks. I didn't see that. Yes, our consequences in risk analysis are quantitatively, we consider life loss and economic cost. Qualitatively, we will consider environmental or cultural consequences for our potential failure modes. So when we evaluate our structures for tolerability of risk, part of one of our tolerable risk guidelines is, are we tolerable from a life safety standpoint? And that gets into our societal risk thresholds and individual risk thresholds. And then for economic loss, cultural losses, or environmental losses, we qualitatively judge, are the impacts significant enough that they would merit potentially national impacts? You know, would they be felt on a national level? So the threshold for economic, environmental, and cultural losses is pretty high, at least for the core. It's pretty high, but we do evaluate all of those different types of consequences individually. All right, well, thank you. I appreciate the questions that you did give.